Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, I have discussed that what is initial liquefaction, and was discussing how to determine the stress required to cause an liquefaction, and we was discussing about the test procedure. Okay, and I have discussed about the stresses on a soil element in two conditions: before the application of ground shaking and after the application of ground shaking. And now I will discuss that how this field condition can be achieved in the test. And then these two tests I am talking about, one is cyclic traction and the cyclic simplicial, and how we can correlate the test results of these two tests, and then we will determine the shear stress required to cause the liquefaction. Okay, so now I was talking about your this initial liquefaction and the field condition. So these are the two conditions at rest and during the ground shaking. And in the initial field condition, when the excess water pressure is equal to initial effective confining pressure, okay, so that is a sigma 3 dash, or Ru is equal to 0. This is Ru. How can you define? Ru is the pore pressure ratio or pore water pressure ratio. So this Ru, how can you define? It is the, for triaxial it is del U by sigma 3 dash, or field this is del U by sigma V 0. Now this sigma 3 dash or sigma V dash is the consolidation test. So stress. So during consolidation, the stress or the is applied or soil is consolidated under this stress condition. Clear? So that's why sometimes it is written at sigma 3 C dash. C means the consolidation. Okay, so this is our initial liquefaction condition, and then we are talking about these stresses. Now we will discuss about the field condition that I have discussed. Now we will talk about the test condition. The first test that I will discuss is the cyclic triaxial test. Okay. Now, if this is a say triaxial sample, okay. So this is a triaxial sample. So we are applying sigma 3, or you can write that sigma 3 dash. So right now I am writing about the sigma 3 only. Okay. So sigma 3 is applying during the consolidation, that is the sigma 3 or sigma 3C. Okay. And there will be a deviatoric stress will apply, that is sigma D. Okay. So this is sigma D is the deviatoric stress. So which is equal to sigma 1 minus sigma 3. Okay. You can write sigma 1 dash minus sigma 3 dash also. So now I am writing this is deviatoric stress. So, and as I have discussed in my previous lectures, that in cyclic triaxial, the sigma 3, the stress during the consolidation, that is constant, and the deviatoric stress is applied cyclically. Okay, so that means here the deviatoric stress will be in the positive or negative or upward or downward. Okay, so that you can see it is acting in the both direction, upward and downward. It is cyclically it is been applied. Now, if we have a condition when suppose this is all round first, then now we again take a soil element. Okay, the initial condition, this is your sigma 3 is applied, sigma 3 is applied, all round pressure. Okay, during consolidation stage. Now in this stage, this in a soil element, all the stresses are sigma 3 is applied. Now if we take two planes, say XX plane and YY plane. Say suppose this is XX plane, this is YY plane. And this plane is making, XX plane is making an angle 45 degree with horizontal. YY plane is also making an angle 45 degree with horizontal. Okay. Now under this condition, what would be the normal stress on this XX plane and YY plane, and what is the shear stress? So we know that we can determine the normal stress sigma is equal to sigma 1 plus sigma 3 divided by 2 plus sigma 1 minus sigma 3 divided by 2 by into cos 2 theta, and shear stress is equal to sigma 1 minus sigma 3 divided by 2 into sin 2 theta, where theta angle is 45 degree. Now if it is 45 degree, then the cos 90, this will be, if I am talking about what would be the normal stress and shear stress on XY plane, and XY plane both are making an angle 45 degree. So theta is 45 degree, 2 theta will be 90, cos 90 will be 0. So the sigma n will be, now here sigma 1 is also sigma 3 and sigma 3 is sigma 3. So it will be sigma 3 plus sigma 3 divided by 2, it will be sigma 3 only. So the on XY plane, the normal stress is sigma 3. Okay. Similarly for XX plane, YY plane, both the plane sigma 3, sigma n, normal stress is sigma 3. Here you can see, but what would be the shear stress in this condition? Again sin 90 is equal to 1, but now sigma 1 is, this is sigma 1 is equal to sigma 3. So this term will be 0. So tau shear stress will be 0. So at XX and YY plane, those planes are making 45 degree with horizontal. So under the consolidation stage, your normal stress on these two planes will be sigma 3 and shear stress will be 0. Because why shear stress will be 0? As your sigma 1 is here under consolidation stage is sigma 3. So that's why this tau is equal to 0. And sigma will be equal to sigma 3. Sigma is the normal stress, or you can write sigma n, normal stress. So this is my first stage. Okay. Now in the second stage, now the loading will be applied. Okay. So in the second stage, we will consider two cases. The first case is the stress on the specimen are changed in the such that the stress on the specimen or stresses are changed such that change such that the axial stress is equal to sigma 3 plus half sigma d and radial stress is equal to sigma 3 minus half sigma d. So that means the stresses on the specimen are changed in such a way or in such that the axial stress is equal to sigma 3 plus half sigma d and radial stress is sigma 3 minus half sigma d, or I should say it is plus minus two cases. So that means one is sigma 3 plus half sigma d and then radial stress will be sigma 3 minus half sigma d. Another case, axial stress will be sigma 3 minus half sigma d and the radial stress will be sigma 3 plus half sigma d. So now if these are the stress condition, then on the same soil specimen or soil element I can draw that now my condition is this axial stress is sigma 3 plus half sigma d. Okay. So here it is sigma 3 minus radial is minus sigma d. This is the first case. So this is the stage 1 with the consolidation stage. Now we are applying the load and the stresses are changed on the specimen in such a way that the axial stress on that element or sigma 1 will be sigma 3 plus half sigma d and the radial stress that will be sigma 3 minus half sigma d. First case. Second case, the sign will change. So now this is the first shear stress condition, sigma 3 plus half sigma d and radial will be sigma 3 minus half sigma d. Now to how I will apply the stress on the specimen, or I will change the stress on the specimen such that this type of stress will act on this element. So that means here I can write, so this is my case 1 where the specimen, it is now sigma 3 plus half sigma d and here it is sigma 3 minus half sigma d. Okay. Now that will be equal to so load, how load is applying? Load is initially sigma 3 was there. Initially sigma 3 was there. This sigma 3 is there. Now we are applying the deviatoric stress. Now if I take the downward, the direction of the deviatoric stress and the sigma 3 is same, then I can write that your vertical stress or the axial stress that will be on this specimen, that will be sigma 3 plus sigma d, because now your sigma d is acting in the same direction of sigma 3. So now this is my loading, but this direction specimen, it is only sigma 3, it is not changing. So this condition I want to achieve, but my loading condition is this, the sigma 3 plus sigma d is acting and but the radial one is sigma 3. Okay. So that means I want to achieve this. So how I have to do? Now this is the actual stress condition. Then plus I can write that plus if stresses are acting in this direction and value is half sigma d, this is also half sigma d, then I can achieve this condition. That is the condition I want to achieve. Okay. So now if you add them, then this will be sigma 3 plus sigma d minus half sigma d. So that means this will be sigma 3 plus half sigma d, and here also sigma 3 minus half sigma d. Okay, so what is this half sigma d? In the second part, this is the pore water pressure that is generated. So that will be half sigma d. So this is the U or the pore water pressure. Okay, so that is your half sigma d. Now here why I am writing minus? Because it is in the negative direction. The positive direction should be towards the element, but it is away from the element. So it is negative direction. That's why finally I can write this is my stress. The axial stress is sigma 3 plus sigma d. Now minus pore water pressure. So that is the effective stress. Okay, minus pore water pressure. So now from here I can write that this is your for the axial stress, that is equal to sigma 3 plus sigma d minus pore water pressure half sigma d. So this is sigma 3 minus plus half sigma d, and for radial initially sigma 3 is there, so that is sigma 3 minus half sigma d. So that is the condition I want to achieve. So that can be achieved in this way. So that means here U is the pore water pressure. So that means the axial stress, this is, there is a total stress minus pore water pressure. So this is sigma 3 minus half sigma d. So this is the effective stress which is acting. Okay. So now if I take the same plane, two planes, XX and YY, same two plane I am taking in this condition. Now here what will be your sigma n on this plane? What will be the sigma n? Sigma n will be your, I can write that now sigma n, now this is 45 degree again, these two planes are 45 degree. So this part will be 0. So this is sigma 1 is now sigma 3 plus half sigma d minus sigma 3 minus half sigma d. So your sigma n will be equal to, in this case 2, this is my case 1, this is case 2. So this is for case 1 or the stage 1, consolidation stage. Okay, now in the loading stage we have case 2. So sigma n will be sigma 3 plus half sigma d plus sigma 3 minus half sigma d divided by 2. So this will be again sigma 3. Okay, and the tau will be equal to now sigma 3 plus half sigma d minus sigma 3 plus half sigma d divided by 2. So this is equal to sigma 3 sigma d is cancelled, half sigma d. So this will be half sigma d. So now shear stress is not 0 because of this applied load. Now stress is generated. Shear stress is generated. Now the question is, why I have taken 45-degree plane? Because where the maximum shear stress will be generated. So I want to determine the maximum shear stress. That's why I have taken the 45-degree plane. Clear? So that I can estimate the maximum shear stress is generated in that plane, or I want to take the plane where maximum shear stress will be generated. Okay. So now here the normal stress is sigma 3. Here also normal stress is sigma 3. But now there will be shear stress. Okay. So there will be shear stress also. There will be shear stress also. Okay. That shear stress value is half sigma d. Okay. The shear stress value is half sigma d. So this way I can satisfy this condition, sigma 3 plus half sigma d and radially sigma 3 minus half sigma d. Now there is a plus minus. Now I will want to satisfy the second condition. Okay, so for the second condition, what is the same element if I take for the second condition, that is my case 3. Okay, so that is also loading condition. Now your axial is sigma 3 minus half sigma d. Sigma 3 minus half sigma d, and the radial one is sigma 3 plus half sigma d. Okay, how I can achieve this condition? You come to the loading condition. So this is my element. Now it is sigma 3 minus half sigma d. This is sigma 3 plus half sigma d. Now my loading will be in the, initially I take that sigma d is positive. Now it is, you can see it is going up and down. Initially I consider the downward. Now I will consider the upward. So that means the sigma d will be negative. But initially there was sigma 3. Okay. So there was the sigma 3. In all round pressure, so sigma 3. Now this will be sigma 3 minus sigma d. This will be sigma 3 minus sigma d, because initially I was taking the positive sigma d. Now I am taking the negative sigma d. Okay. So that if I add, then the pore water pressure will be how much? The pore water pressure will be equal to, because I have to satisfy this condition, sigma 3 minus half sigma d. Now here it is sigma 3 minus sigma d. So I have to consider sigma 3 minus half sigma d. So I have to add a u value, that is half sigma d. So there will be a positive pore water pressure. So here u will be half positive now, sigma d. Now if you the same way, axial stress will be sigma 3 minus sigma d plus half sigma d. So that will be sigma 3 minus half sigma d, and this will be sigma 3 plus half sigma d. So this is sigma 3 plus half sigma d, sigma 3 minus half sigma d. So this way I can achieve this. Now again, if I consider the two planes, that is the again yy and xx plane. Now, what will be the normal stress now? Normal stress will be here only the this sigma 3 minus half sigma d plus sigma 3, this will be plus half sigma d, the same, only the sign are changing. So, here normal stress there will be no change. Normal stress it will be sigma 3 minus half sigma d plus sigma 3 plus half sigma d. So, for the normal stress I am just writing, changing the sign. This will be, sorry, this will be minus, this will be plus. Remaining thing will be same. So, again, so that means here this will be sigma 3. Okay. So, this will be sigma 3. So, for this normal stress again will be sigma 3, both the planes. Okay. What about now the shear stress? What about the shear stress? Shear stress will be sigma 3 minus sigma d, half sigma d, then minus sigma 3 minus half sigma d. Okay, because now it is sigma 3 plus half sigma d. So, it will be sigma 3 minus half sigma d minus sigma 3 minus half sigma d. So, again this sigma 3 will cancel, only again the shear stress will be sigma d, half sigma d, but the sign will change or the direction of the stress will change in the case 3. So, this will be, I can write minus, and in if it is positive, red color is for case 2 and for this blue color is for case 3. So, now the sigma 3 shear stress value will remain same, but the direction will change. So, now its direction will change. Okay. So, value will same as half sigma d. Initial value will also, here also values were, this value was half sigma d, here also value is half sigma d, only the direction of shear stress is changing. So, now in the case 2 and case 3 on the plane of xy and yy and xs, normal stress will remain same, shear stress value will remain same, but the direction of shear stress will change. Clear? So, and how I can achieve these two conditions? First condition is the consolidation condition. On the second two condition under loading condition. So, how in these two condition I can achieve during the loading or during changing the stress on the specimen, that also I have discussed in this side. Here also this is the actual loading and this is the pore water pressure, and this is also loading, this is the pore water pressure, and one is the positive pore water pressure and this is the negative pore water pressure will develop, and then we will achieve these two conditions. Okay. So, now this is my triaxial test. Now, I will go to the simple shear test, cyclic simple shear test. Okay. Okay, cycle simple shear stress, as I have mentioned in previous class also when I was when I discuss about the cyclic simple shear stress, because in this test the field condition can be easily simulated as compared to the triaxial test. So, field condition I have discussed in my previous lecture. So, this is the field condition. Now, that can easily be simulated here, because here my condition is that for a soil element, say before applying the shaking, this is the sigma V bar or dash, and again this will be K0 sigma V bar, like this. Okay, same for a soil. Okay, and now this is a soil element. Under this condition, if I draw the Mohr circle, under this condition, if I draw the Mohr circle, this is sigma n, this is tau. If I draw the Mohr circle or half Mohr circle, then this will be your sigma V dash, this will be your sigma K0 sigma V dash. Clear? Now how I will get the radius? The value of this radius of this circle is half sigma V dash minus K0 sigma V dash, or I can write half sigma V dash 1 minus K0, that is this radius. So this is my first or initial condition or the at rest condition, which is same as the field. Now here the same soil element, now the loading will apply or the shearing will apply. Okay, so now this is sigma V dash, this one K0 sigma V dash, this is, so initially shear stress, there is no shear stress on this plane. Now the shear stress will develop, so that is on the plane due to the shearing. Okay, now the shear stress will develop. So now if I draw the Mohr circle, and the second case, tau. So these are 2 points, that is sigma V dash, K0 sigma V dash, this is the center, this is the same initial circle, position of same initial circle. But now on this plane, the shear stress is developed, but your sigma normal stress, that is same, that is not changing on the plane. Normal stress is not changing, only the shear stress is changing, or there is a development of the shear stress. So now I can take the coordinate on the circle. So this is one point and this will be the another point. So what will be the coordinate? This point will be sigma V dash in comma tau z, tau h, this is developed shear stress, and this one is, this point will be K0 sigma V dash minus tau h. I can locate these 2 points. Now join these 2 points, will pass to the origin. Now draw the circle. Okay. Clear? Similarly, here also you can complete the circle. Now, what is the maximum shear stress here? The maximum shear stress is this one. This is my tau max. So, this is the maximum shear stress. Okay. So, this one is tau max, which is the maximum shear stress. Clear? So, now in this triangle, if I complete this triangle, that is triangle say O, A, B. Now triangle OAB, now OA is tau max, Okay, that is the same, this distance tau max, and this one is tau h. That means AB will be tau h, and OB is how much? OB is same, this radius, OB is this one, this is also OB basically. OB is this one, so OB will be half sigma B dash 1 minus K0. So from this triangle I can get the tau max, that will be root over, actually basically OA square is equal to AB square plus OB square. So OA will be root over AB square plus OB square. Now AB is tau h square and OB is half sigma V dash 1 minus K0, that is whole square. So this way I can get the tau max value also. Okay, later on I will use these values, tau h, tau max, sigma V bar, or half sigma d, sigma 3, those I will use later on. So this way I will get the tau max. So now I have discussed that under cyclic triaxial condition and cyclic simple shear condition, how the stresses are developed in different plane. Okay, now I have to correlate them. Okay, in the next class I will discuss how I will correlate these two test data, and from there I will determine the stress required to cause the liquefaction. Okay, so in the next class I will discuss how I will correlate these two test data, and then I will correlate that test data to the field data, and from there I will determine the shear stress required to cause the liquefaction. Thank you.